Okay, the second example is, or this example is about solving for I1, I2, and I3 of the given circuit. This is a simple example, quite simple one, but the idea is to assure some concepts before we do some of the a little bit more complicated examples. So to solve this circuit, we have two or three or even more ways. The first way is actually to apply KVL KCL. We have a current that comes to this node, then it splits into two currents. So we have I1 equal I2 plus I3. So we have one equation with three unknowns. We need two more unknowns. The second and third equations can come from KVL. So we have one loop here, and we have two loops outside. This is one with the outer resistance, with the inner resistance, and this is one with the outer resistance. We can choose any of these loops. For the one inside, so I'm talking about this one. Okay, this loop actually can be looked in a different way. It can be thought of, okay, we have two parallel resistances, this resistance and this resistance. They are in parallel. They have the same voltage, which is indicated here as V2. Okay, this is the same. It is actually the same result if whether you write it as a loop equation like this. I am going from this point. I'm making counterclockwise a loop. Sorry, this is clockwise a loop. So minus 10 kiloamps times the current I2 plus the 40 kiloamps times the current I3 equals 0. So this is one way of writing this second equation. Or if we say, okay, this voltage here is the same as this voltage here because they are in parallel. The voltage here is I3 times 40 kilo ohms, while that equal the same voltage there, which is I2 times 10 kilo ohms. This is the same thing actually. These two things are exactly the same thing. If we take this to the other side, we get this. So if we divide this by 10, we get that 4 multiplied by I3 equal I2. In other words, I2 is bigger 4 times than I3. And that is a logical result because I2 is smaller, R2, the resistance R2 is smaller 4 times than the resistance R4. So we are expecting that this current I2 be bigger 4 times than this current I3. Okay, so this is equation number 2, or the result of equation number 2. Equation number 3 can be any of the loops. We can take the inner loop. Okay, minus 48 equals, minus 48 plus the voltage drop V1 and the voltage drop V2. So this is voltage rise. The 48 is voltage rise. This is voltage drop, and that is I1 multiplied by 12 kilo ohms plus I2 multiplied by 10 kilo ohms. And this is equation, no, the whole thing is equal 0, and this is, I guess I am out of space, so I will just pull up this equation, guys. Okay, once again. Alright, this is better. And this is equation number 3. Okay, Now, if we rearrange and if I rearrange and put things a little bit in a neater way, so this is after some cleaning up, we get these three equations. Now these are simple equations. There are different ways of solving them. For this one, it is much easier to substitute actually. Just take this equation, equation number 2, substitute it in equation number 1, and the result to be substituted in equation number 3, and we end up with one of the currents. Then we find the other one, and so on. So let's try to do that. Now, equation number 2 says that I2 is 4 times R3. That means that I3 is 1 over 4 I2. Okay, since that's the case, we put that back in equation number 1, and we get that I1 equals I2 plus 1/4 of I2. Okay, so I1 equal 1.25 I2. Now we can put this here, right? And we get that 1.25 I2 multiplied by 12 kilo ohm plus 10 I2 equal 48, 10 kilo ohm, please don't forget. So I2 would be 48 divided by 25, and that equals 1.92 milliampere, because this is kilo ohm. Don't forget that. Okay, so we found I2. Now we substitute here, and we substitute here, and we get I3 and I1. So from there, I3 is 1/4 of I2. So if we divide 1.92 milliamps over 4, and that means that I1 equals the total of these two currents, I2 and I3. So I1, maybe here, I1 equals 1.92 plus 0.48, and that equals 2.4 milliamps. So this is one way of solving this problem.